Okay, let's wait for 1 minute for your friends to join. Okay, so let's continue to the FCC now. So we did two calculations for calculating the packing fraction or the the packing fraction we already found for simple cubic it is 0.52 or 52%, and for the body centered cubic it came out to be 64% or 0.64. Now we need to do it for the FCC. So how do we find out the R now? You tell me, guys. Can some of you find out the R now? What will be the R for this calculation? You see, let me just go to the presentation mode. Yeah. Right. So here now, this is, we'll say A, the side of the cube, and here this part is R, right? From here to here, right? This part is R. So now, how will you find out the relation between R and A, right? Can someone tell me now, how will you do this? Can someone tell me, or try, tell me how much it be? So now this one is actually simpler. If you look at it now, this is R, right? That means if I draw a line now through the face rather than the, oh my God, this would have been straight line, but let me just remove this. Let me just remove this. All right, it should be a straight line, of course. Let me pick up the pen. So you see now the connection is through the face. Previously it was through the body. Now it is through the face. That makes life easier for us. So you see now, this is something like this. So what is happening here now? This is R. This is the diameter. So this is 2R and this is R, right? It makes it easy. And these of course are A and A. This is A and this is A. So again from Pythagoras theorem, what will we say? That R plus twice R plus R, that is 4R. That means 4R squared is equal to A squared plus A squared, right? So it will be 16R squared is equal to twice A squared, or R squared is equal to 1 by 8 a square, correct? Now we take the square root, r equal to 1 by 2 root 2a. You know how I got this 2 root 2, right? So it is 8 is actually 2 cube, right? So it is 2 cube. So you're taking square root. So if you can put this as 1 by 2 square into 2. So for this 2 square, I'm getting a 2, and for this, I'm getting a root 2, right? So this is 1 by 2 root 2 a. So rest is the same now. How many atoms we have inside now? We have 4 atoms now, right? 4 atoms inside. So calculate the volume of one atom like before. So if I have volume of one atom multiplied by 4, I get the fraction that is inside. That means the volume of that is divided by the volume of the cube. Okay. If you do this, you should get about 0.74. I think the answer is that. Yeah, 0.74, as you can see here. You get 0.74. All right, so these calculations you need to do. Okay, you tried it out. I'll give you a couple of more complex ones, but as far as your exams are concerned, I think these cubic structures, if you can calculate well, you might expect one of these to come in your exams. So you should try these. They're very not very difficult, very simple mathematics, but you should be confident when you're doing it. Okay. All right. So let's move ahead. Like you see now we are moving to some complex type of structures now. So this is hexagonal closed pack structure. Okay. So here the structure is very unique. All right. Like you see there are 3 planes here, hexagonal planes. Okay. That means 6 sides. And if you see here the top one has 7 atoms, bottom one has 7 atoms, but the intermediate one has 3 atoms. All right. And they are inside. Okay. They're inside. That means when you're considering the atoms, all these atoms will be sharing with other unit cells, but these 3 will not share with other unit cells because they're inside the unit cell. All right, like your body standard cubic, there you had 1 inside, here we have 3 inside. Okay, but this is a bit complex, so we won't go for all those calculations, but this is one type of structure where the alpha, beta, and gamma, they are given. All right, they are not same, as you can see. 2 sides are same, A and B, but it's not equal to C. Similarly, alpha and beta are same on 90 degrees, but the gamma is 120 degrees. All right, so these are different variations. This is how a crystal varies. Okay, this is just for your knowledge that this type of crystals can also be there as unit cells can be like this for different crystals. Okay. So as a comparison, it's very difficult to visualize, but if you think this is a top view of a hexagonal closed pack, and this is a face-centered cubic. You look at this and think for some time later and try to visualize and see if you exactly see what we were talking about till now. Okay. So this is the calculations that I already did for you. So this is just for your use later as to how you go to the radius from A. Okay. So relating all these crystal structures, we come up with some indices or some values which we express as H, K, and L as far as your crystal is concerned, okay, which are called as the Miller indices, mainly because it was it was formulated by a person called Miller. Okay, so let me stop the video. Yeah, so the Miller indices basically talk about a crystal. So those values that we are talking about, the lattice parameters, they finally relate to the Miller indices. Okay, so the Miller index is a crystallographic notation. Okay, so we use them as H, K, and L. Then they are integral values. Okay, I mean they are integers. So how do you calculate them? Miller indices are integers that are inversely proportional to the intercepts of the crystal face or crystallographic planes with the edges of the unit cell. So where the faces actually cut the unit cell. Based on that, we do the calculation. It is the reciprocal. That means it is inverse, 1 by the length where it cuts the crystal, okay? And then it is easier for us to represent a crystal, okay? We say the planes are designated by HKL. This is the first bracket, right? The first bracket, we said. Then we are talking about the planes. Okay, I'll explain this further. Say we are talking about, say, suppose 001 is the HKL. Then we call it as a plane 001, and this 001 can have multiple planes because all parallel planes are considered to be the same. All right. That means if I talk about any crystal, even say I'm talking about this one. So this is one plane, right? So all these planes above parallel to this will be considered as the same plane. Okay, they will all have the same Miller indices. Like this plane here, if I put another unit cell here, I will have another plane on this side and another plane on this side. It will continue like that. So all these planes which are parallel to each other will have the same Miller indices. Okay. In fact, you can cut a plane like this also from the center. So it's up to you how you cut a unit cell. You can slice it in any way you want, but no matter in which direction you cut, you will have parallel planes in that direction all throughout the crystal, and all will have the same Miller indices. Okay. So we use, when we're talking about these planes, then we say we use the first bracket. All right. So family of planes designated with this one, like I told you, one plane can have multiple parallel planes, then we call it as a family. So if we are talking about the whole family, we will use these brackets, either this bracket or this one. And if you're talking about one single plane, we will use this one. Directions designated with square brackets. Now, if you talk about direction, now what is the direction here? Direction basically talks about the direction that the parallel planes appear in. That means if I say this one, and if I say that this one has a Miller index of 001, suppose as an example, then I'll say the next one also will have 001, next one also have, all the parallel planes will have. So the direction will be moving up like this. So if this plane is 001, then this direction is 001. Okay, you understand? So the perpendicular to the face, and that is expressed by these square brackets. All right. So this one is for a single plane, this one is for a parallel planes as a family, and this one is for the direction perpendicular to this plane. That means if I say a right direction like this, I will automatically mean this is the direction perpendicular to this plane. Okay, so that is how we use Miller indices to express or talk about a particular unit cell. Okay, so this is how we do the calculation. You say place the unit cell at the origin. Okay, that means one corner of the unit cell we will consider to be the 0, 0, 0, 0 point. All right, and then we do the calculations. So place the unit cell at origin 0, 0, 0 of the Cartesian coordinate system. So it's a Cartesian coordinate system of a 3-dimension, right? X, Y, and Z. Determine intercepts of the plane faces along the crystallographic axis in terms of normalized unit cell. I'll show you an example. Okay, that means ABC we already have as the lattice parameters. So based on which part of A the crystal cuts or which part of B the crystal cuts, we'll do the calculations, okay? And take reciprocals of these intercepts and to get our Miller indices, right? So suppose the unit cell cuts the axis at A, B, and C, then the Miller indices will be 1 by A, 1 by B, and 1 by C. But this has to be a integer, right? I already told you. This has to be a integer. You know what is the integer, right? 1, 2, 3, 4, all these are integers. That means it cannot remain as a fraction. That means if it remains as a fraction, then you need to multiply with something to get it. As an example, I am suppose giving this as, suppose this is 1 by 3, 1 by 3 and 2 by 3. Suppose you are getting these values on calculation. Then when you make 1 by A, 1 by 1 by C, that means suppose the unit cell is cutting at 3, 3 and 3 by 2. Then you get this one, but you cannot use this as a Miller indices. What you will do, all that you have 3 below, so you multiply with 3 and you get 3, 3, 2, right? Sorry, 6. But then you can bring it down because you see these are all divisible by 3, so your Miller indices will be actually 1, 1 and 2. Okay, that means if your calculations give you these values, your Miller indices will be 1, 1 and 2. Okay, I hope this is clear. Otherwise, we'll discuss again. You can try that out. It's not very difficult. So if a plane does not intercept, we are talking about parallel planes, right? So parallel planes will never cut each other, right? So if they never cut, then the intercept will be infinity, right? It will never cut. So then the Miller index calculation will be 1 by infinity, which will give you a 0. All right. So if fractions result from reciprocals, clear all fractions. That's what I showed you, no? Clear all fractions and make it into integers. So multiply by common divisor to obtain smallest integers. Okay. So here we multiply, but we got this is not the smallest integer. The smallest integers will be 1, 1 and 2. Okay. So this is an example they also gave. They gave 1 by 3, 2 by 3 and 1. All right. So here then you are multiplying by 3. So if you are multiplying by 3, this becomes 1. Multiply by 3, this becomes 2. Multiply by 3, this becomes 3. And that's why scale will be 1, 2 and 3. All right. Reduce to lowest terms and replace negative numbers with a bar over the number. All right. So reduce to lowest term means this what we did here. 336 was reduced to 112. All right. Now if there was a negative number here, that means if we had been minus 3, 3 and 6, then when we're writing the Miller indices, we don't write minus, but we put a bar on top like this. Right. That's how we represent it. So if we give the Miller indices, anybody can immediately recreate the crystal. Okay. And this is the point I was talking about. All parallel planes are identical. And all parallel planes will have the same Miller indices. All right. Because they will be simply integral multiples in different directions. Okay. So integral multiples, when you bring them down to the lowest value. All right. Is this too much of mathematics for you guys? Getting it difficult? Okay, somebody tell me, are you really understanding what I am talking about for the last 1.5 hours? Is this clear a little bit? Anybody? I want to hear from someone that is, yeah, understandable or it's totally gone over the head. Someone?
Little bit, sir. Little bit.
Little bit you understood. Okay, at least you are not saying you did not understand anything. All right. So now, of course, because I'm teaching at the moment and you are just listening. So now once you sit down and try out a few of these, it will be even more clearer. Of course, I will be sending out some notes for all of you for your help. All right. But the idea is that we try to understand the crystals, the simple structures, and we get a feeling, an understanding of how actually atoms are aligning themselves in these crystals, and how, if we tightly pack them up, what amount of volume is occupied by them of the total volume of the unit cell. So basically that is what we are discussing in today's classes. So what I will do is I will leave you guys here because I have to rush to the university now because I'm working from home at the moment, but I've been called to the university. So I should reach there by 11. So any questions you have till now on this? Let me, what is next? Okay, quickly let me show you this one now on the talking of the Miller. See, this we say what we first put the Miller's the unit cell in the origin. So this is the origin of the x, y and z axis. Consider this to be the origin. That means this particular point of this crystal is 0, 0, 0. All right, now look at the situation on the atoms. If you go this way now, this is exactly at the corner of 1 unit cell. All right, that means if I move up here, this is moving up only in the z direction 1 unit, but x and y direction it is at the same position, that is 0, right? And that's why this one will have a locational value of 0, 0 and 1. It is one step on the z-axis. All right, similarly this point is one step in the x-axis but 0 steps in the y and z-axis. All right, so it is having the x value has changed 1, 0, 0. This one is 1, 0, 0. Now this one, okay, it is a face centered one. Say suppose in the face, all right, then face will be half of it, right? So this is 1, then in the x direction it has moved half. All right, in the y direction it has not moved at all, and in the z direction it has moved half, and that's why it is half, 0, half. Now if you have one at the center of the cube, all right, like if we talk about the body center, this is a face centered situation, this is a body centered situation. Now you see here what is happening. Say this is your 0, 0, 0 origin. Now to come here, because this is exactly at the center, all right, and a unit cell length is 1 we are considering, then it will go halfway here, and halfway here, right, to get to the center. That's why the coordinates are half, half and half. Think about this one now. We are here now when it's 0, 0, 0, all right, so this is the x direction. We are not moving in the x direction, is still 0. Y direction we are moving 1. Z direction we are moving 1. That's why this value has 0, 1, 1. Consider this one now. Okay, this corner. So this corner means this is just above this one. So we are moving in all the directions. Now x is 1. Move to y is 1. Move to z, that is 1. And that's why this is 1, 1, 1. Okay. So that's how we do the calculations. Is it okay? So students, what I'll do is I'll stop here at the moment. I'll quickly get ready and go to the university. So you please try out these that I had given you. All right, complete those problems that we had done half, right? Do the final calculations and see if you get the answers. The answers are already given to you. So basically it's like 52%, then we have 68%, and then we have 74%, all right, for the three different types of you say cubic structures, right? So kindly try those, all right? You don't have to send to me, but it will be comfortable if you can do them, because you might be asked in the exam. I don't know whatever exam we will have, but whatever, we'll try to see, but those might be important for your exams, okay? So all right, then I'll stop here. You kindly send me your attendance, all right? I'll give you one more class because we missed yesterday's class. Let's find the time suitable where we can have one more class this week. All right? Okay. Thank you, guys. Okay. Bye.